Donc we're going to do exercise 7 in the third sheet, which was to classify up to conjugation all elementary Fuchsian groups. Okay, so it's elementary. So it has, we're assuming that it has a finite orbit somewhere in the closure of the hyperbolic frame. So the first case I'm going to look at is the one where gamma contains a parabolic element. And this parabolic element I'm going to denote it by small gamma. Okay? Now, small gamma is conjugate to z goes to z plus a, which has one finite orbit, which is infinity. Okay, so I know now that the finite orbit of big gamma is infinity. Okay, so no elliptic element fixes infinity, and so gamma has no elliptic elements, and a Fuchsian group cannot contain a parabolic and hyperbolic element with the same fixed point. We already saw that if you had a parabolic and hyperbolic element with the same fixed point, we could generate a non-discrete subgroup using those. So in that case, gamma is contained in the set of parabolic elements fixing infinity. So gamma is a discrete subgroup of the set of elements of the form z goes to z plus a. So we've completely understood the elementary subgroups that contain at least one parabolic element. So now, we know that what happens if there's a parabolic element. Let's suppose that there aren't any. Next case is that I have no parabolic elements and no hyperbolic elements. So case 2, gamma has no parabolic or hyperbolic elements. Well, we already saw that if I had two elliptic elements with different fixed points, I could always, using those, generate a parabolic or a hyperbolic element. And so this implies that there exists a fixed point, let's call it P in H, such that gamma is a discrete subgroup of the set of points P, the set of points of gamma, such that gamma of P is equal to P, and obviously this implies that gamma is elliptic, so this gives me that gamma is isomorphic to a discrete subgroup of U1. And the final case I have to deal with is the one where gamma has at least one hyperbolic element. Okay, case 3, which is going to be gamma has a hyperbolic element, which I'm going to call gamma. Okay? Now, after conjugation, we assume that the fixed points of gamma are 0 and infinity, and that gamma is of the form z goes to lambda z, and I notice that the only finite orbits are subsets of 0 plus infinity. Okay, so now case 3a is the finite orbit is a subset, a 1-point set, and I'm going to suppose that after conjugation, the finite orbit is infinity. Okay? So, we know that we cannot have any parabolic elements in our subset because it contains a hyperbolic element. We're asking for things that fix infinity, so we can't have any elliptic elements. So, we have that gamma is uniquely hyperbolic. Okay, so I claim, and I'm assuming that z goes to lambda z is contained in gamma for some. So this should be big gamma here, contained in gamma for some lambda different from 1. And I claim that in that case, gamma is contained in the set of things of the form z goes to lambda times z. Why not? If not, there exists another element of the form z goes to uz plus a, with a different from 0 and u different from 1. Okay? But then, I can conjugate these two hyperbolic elements and I take z goes to lambda z goes to mu lambda z plus a, and then I divide by lambda goes to mu z plus a upon lambda, so this has to be contained in gamma, and what I get is that z goes to mu z plus a lambda to the n is contained in gamma for all n. And this is a contradiction because this is not discrete. Okay? Okay, so this gives me that gamma is of the form, all the things of the form z goes to lambda z, all the objects of the Poisson lambda. Okay. So case 3b is this one where the finite orbit is 0 plus infinity. And if gamma is entirely hyperbolic, we're done. We've already kept. Done. Okay, so we may assume that lambda gamma contains, on that we're going to call it alpha, an elliptic element. And I have to have that I know that alpha has to take 0 to plus infinity and plus infinity to 0, so I have that alpha is of the form z goes to minus b over z, and conjugating, we may assume that alpha take z to minus 1 over z. Now, suppose that beta taking z to minus mu over z is also in gamma. Okay? Then I would have that z goes to minus mu over z goes to minus lambda mu all upon z. Now I'm going to multiply this by I'm going to compose this as z goes to minus 1 upon z. So this is, here I have beta, here I have z goes to lambda zeta z, and now I'm going to compose this with alpha goes to z over lambda mu, and this is contained in gamma. Now, I know that the hyperbolic elements of gamma are all of the form z goes to lambda to the power n of gamma, so this tells me that mu lambda is of the form lambda to the power k plus 1, and therefore mu is an integral power of lambda. So what I get at the end is that gamma is conjugate to the thing developed, the space generated by z goes to lambda z and z goes to minus 1 upon z.